Okay, this one's a two-part problem, and we have two wires and then a point P. It's important to keep in mind that point P doesn't have like a wire there or a charge there or anything like that. It's just a point in space. The distances D are the same and are listed in the problem. So your objective will be in part A to find a magnetic field at one location, and part B to find the magnetic field at a different location. Okay, good luck. Come on back if you need help. I'm going to get started. Let's see. Let's start with part A. I've blown this up so that we can get a better sense of the geometry here. Okay, so we are interested in the magnetic field at a point directly in between these two, and that's going to be at a distance r equals d over 2, half of d, right? That's half of d from this wire and half of d from this wire. Okay, so if we know that the currents are both out of the page, and we do, because they're indicated by the dots instead of the x's, then we could go ahead and sort of sketch the magnetic field from each of these. So the magnetic field due to the wire on the left is going to be pointed, according to the second right-hand rule, is going to be pointed this way, and therefore should be pointed upward at the midpoint. Now wire 2 is going to have the exact same system because it is also a wire pointed out of the board. So it should also have a magnetic field that is given as counterclockwise from our point of view, and therefore we'll have a magnetic field that is pointed down at the point of interest. I'm going to go ahead and make that a little out of the way there so that it's easier to see everything. Okay, so that means that one of ours is in the positive y direction and one is in the negative y direction. Let's determine how much each one is. Alright, the magnetic field due to wire 1 is given as mu naught I over 2 pi times the distance away, which we know to be d over 2. That is the current 1. The magnetic field due to current 1 should of course contain current 1. And that gives us, we can go ahead and replace here d over 2. We know what d is. D is actually 20 centimeters, so we can list that as 10 centimeters, right? Or 0.1 meters. And that gives us a value of 6 microtesla. Our direction on that is positive y hat direction, so we can actually list that then as a vector. For the B field due to wire 2, same process, right? We'll get 2e negative 7, and it's just because of the mu naught canceling the 2 pi here. We get 5 amps of current, I think. Yes, 5 amps. Same distance. And that gives us 10 microtesla, but that's in the negative y hat direction. So the total for part A is going to be simply the sum of these two, or negative 4 microtesla in the y hat direction. Okay, let's go through that same process again, but this time we're going to focus on point P. Okay, so for this process, it's not that hard for us to find the magnetic field due to the presence of wire 1. We go through that same process, but we extend the ring of magnetic field all the way to point P in this case. And again, we have this counterclockwise directionality to our field. But we need to go ahead and look at the field due to wire 1 as well. And that one is extended quite a bit farther, right? And has a different direction. Okay, so let's take a moment to figure out what that direction is. Of course, the directionality is still the same. So our objective is to figure out what direction our arrows are at point P. Okay, because of this, we know that our field due to wire 2 has an arrow pointed to the left, so that's no problem, and we can even write up here an arrow to the left representing that vector. I'll move that down a little bit. Okay. We can also find a arrow to represent the magnetic field due to wire 1. And if you think about it, then you should have a radial distance that is exactly 45 degrees, since we get d distance away, or 20 centimeters to the right and then 20 centimeters up. We know that this angle is 45 degrees. And so if that is a 45 degree angle distance-wise, then that means that our arrow then must be perpendicular by the definition of a circle, essentially. And so we get some arrow here that is at a 45 degree angle. We do not know the magnitude of that arrow, but that is the way that we put the vectors together visually so that we can calculate them. Now we're going to need to, with this vector math, so we're going to have to be careful with this. We want to essentially add together the x component of this one with the x component of the brighter purple, and then the y component, of course, is all by its lonesome. Alright, so let's do this again. We'll go through the process of finding the magnetic field. This time we'll start with wire 2 because it's simpler. Again, we have a distance that's a little bit simple. We're going to have, let's start off with mu naught I2 over 2 pi times the distance, and that's this time simply d. So that gives us wire 2 carries 5 amps, and we have a distance of 20 centimeters, so 0.2. We also have a direction on this. It's going to be in the negative x hat direction. Okay. And that gives us negative 5 microtesla in the x hat direction. Alright, let's try this again with 1, but this time we're going to have to put part of it in the x hat direction and part of it in the y hat direction. Alrighty. To find the x component, what we need to do is first do our magnitude. So what is the magnitude of the B field due to wire 1? Well, this is going to be, first of all, we need to find out what this distance is. And by the Pythagorean theorem, if this is d and this is also d, then our distance here, r, should be equal to d squared plus d squared. If you plug in your value for 20 centimeters here, or 0.2 meters would be a better way to do that, then you should end up with about 0.283 meters, about 28.3 centimeters from this point to this point. Okay, so we have that distance. Let's go about our process again. Mu naught I1 this time over 2 pi times 0.283 meters. Remember, current 1 is listed as 3 amps. This is going to give us a magnitude, total magnitude. This arrow right here, this purple arrow here, is represented by this number. So we can actually draw these out as soon as I get out my values, so that we'll be clear about what we mean. I get 2.12 microtesla. It doesn't have a direction, it's just a magnitude. Let me clear out this bit. Okay, so what that means is we can label this as 2.12 microtesla, and we'll label the other one as 5 microtesla magnitude, right? Our objective is to figure out how much of the shadow of this one matches this one, right? So we need the x component. In order to find the x component, we know this is at a 45 degree angle. This is 45 degrees here, right? So what is going to be our x component and what is going to be our y component? Well, the x component of this is going to be given by 2.12 microtesla times the cosine of 45 degrees. Same for the y component, because we have the lucky situation that it's at 45 degrees, it should end up with the same number. and that is 1.5 microtesla for each. Now we can actually talk about whether these are negative or positive, because we actually have a single axis to work with. So is the x component negative or positive? Well, this thing is pointed up and to the left. It's not pointed up and to the right, it's pointed up and to the left, and therefore the x component is going to be negative. It's pointed up and to the left, it's not pointed down into the left, it's pointed up and to the left, so the y component is going to be positive. Okay, so now we can fill in this bit. Here we have a negative 1.5 microtesla in the x-hat direction, and a positive 1.5 microtesla in the y-hat direction. So that gives us then a total. Remember, this magnetic field due to wire 2 is entirely in the x-hat direction. We will add that to this x-hat component, but not to the y-hat component. This is left all by itself. So the total magnetic field in vector form will be negative 6.5 microtesla in the x-hat direction plus 1.5 microtesla in the y-hat direction. Okay. Box that in. Alright, I'm going to clean this up. And those are the values I get for parts A and B in vector form. If you got a different answer, go back and see where either you messed up or I messed up.